Welcome back, focused learners, to today's explainer. We're diving into the absolute rulebook for the speed of the universe, which is chemical kinetics. You know, thermodynamics tells us that diamonds are technically constantly turning into pencil lead. Sounds crazy, right? But kinetics steps in and says, yeah, but that process is going to take billions of years. If you've ever wondered why a firecracker explodes in a split second but a piece of iron takes literal decades to rust, well, you're in exactly the right place. Okay, let's dive into this. This is the ultimate dividing line between two massive fields of science. Thermodynamics is all about the if. Can this reaction happen based on energy? Sure. But kinetics? Kinetics is the thriller movie of chemistry. It's a race against time, asking exactly how fast that possibility becomes a physical reality. So here's our roadmap for this explainer. First step, the baseline. Then we'll look at the controllers. From there, we zoom into the micromechanics, followed by the math, and we'll wrap it all up with the real world. All right, let's kick things off with section 1, the baseline, measuring the speed of chemistry. At its core, the rate of a chemical reaction is just the change in concentration of your reactants or products over a specific unit of time. Think of it exactly like measuring the speed of your car in miles per hour down the highway, except here, our miles are the amounts of chemicals in a flask. We're literally just watching the clock and tracking what vanishes and what magically appears. When you actually run the math on these rates, you're going to see positive and negative signs pop up. And listen, that negative sign isn't just some abstract algebra rule. It represents the physical disappearance of your reactants right before your eyes. They are being consumed. The positive sign? That means fresh products are actively being born into existence. And our standard speed limit for all this action? That'll be moles per liter per second. Now, we've got two different ways to measure this chemical speed. First is the average rate, which is just the change over a specific block of time, kind of like calculating your overall average speed after a long 3-hour road trip. Then you have the instantaneous rate. This is the speed at a specific, exact freeze frame moment. It's the chemical equivalent of a cop hitting you with a radar gun, and mathematically, it's the exact slope of the tangent line on your concentration graph. Let's move to section 2 and see how this builds. The controllers, how we manipulate speed. I want you to consider these 4 physical controllers as your personal chemical toolkit for hacking a reaction speed. Number 1, concentration. Pack in more molecules, you're absolutely going to get more collisions. 2, temperature. Crank up that heat and you pump up the kinetic energy. 3, catalysts. These are those sneaky little additions that lower the energy barrier without actually being consumed themselves. And finally, surface area. Chop something up to create more contact area and boom, you get a much faster reaction. It's exactly why you have to chew your food. But we also have to look at the very nature of the reactants we're playing with. Ionic reactions, those are typically lightning fast. We're talking almost explosive flashes. Imagine mixing 2 clear liquids that instantly turn into a cloudy solid. Covalent reactions, on the other hand, are inherently slow. Think of that iron rusting over geological timeframes. The literal materials you start with lay down the absolute baseline limits of your speed. Okay, time to zoom way in. Section 3, the micromechanics, peering into the molecular world. So the crucial point is that for a reaction to actually happen, collision theory demands that 3 strict, mandatory rules are met. First off, the molecules absolutely must physically collide. Second, they have to smash into each other with sufficient energy. And third, they need the proper orientation. It's literally like 2 puzzle pieces floating in space. If they aren't facing the exact right way when they crash together, they just bounce off. Nothing happens. Let's look a little closer at that second rule, the sufficient energy part. In chemistry, we call this the activation energy. You can think of it as this massive invisible hurdle that your molecules physically have to jump over to transform into products. If they don't have enough kinetic energy in the tank to clear that hurdle, the reaction just completely fails. So what happens right at the very top of that hurdle? Well, transition state theory tells us that for a fleeting, incredibly unstable moment, the reactants form what's called an activated complex. Picture a pole vaulter suspended right over the bar. They're definitely not on the ground anymore, but they haven't landed on the mat either. It's this high-tension, in-between state right before they finally convert into the end product. All right, let's shift gears. Section 4, the math, predicting the unseen. Here we have the fundamental rate law expression. Basically, the rate equals our rate constant, K, multiplied by the concentration of our reactants, which are raised to the powers of m and n. Now pay close attention to those powers. Those are the orders of reaction. And here's the kicker. They are experimentally determined secrets. You absolutely cannot just pull those numbers from a balanced equation on a whiteboard. You have to get in the lab and physically run the experiment to find them. Now, what's really interesting here is this ultimate cheat sheet for integrated rate laws. Notice how the graphs completely change their shape based on the reaction order. If you've got a zero-order reaction, the rate is totally independent of concentration. It's like a bouncer at a club letting exactly one person in per minute, no matter if there's 10 people in line or 10,000. That gives you a nice straight line on a standard graph. First order, that only gives you a straight line when you plot the natural log of the concentration. And second order spits out a curve. If you memorize these distinct shapes, you can literally just glance at raw data and instantly identify the reaction order. It's a total superpower. Let's tie this math right back to our physical toolkit using the Arrhenius equation. Just look at the variables here. EA is our activation energy, and T is our temperature. This formula is brilliant because it mathematically proves exactly what we already intuitively know. When you crank up the temperature, that rate constant K gets larger. Guys, this is literally the mathematical proof of heat speeding up the universe. Now, we really need to draw a hard line between two terms that constantly trip people up: order and molecularity. Order is the experimental reality. It can absolutely be a fraction, and it applies to the overall speed of the reaction. Molecularity, though, that is purely theoretical. It's just the number of molecules involved in one single elementary step of the reaction mechanism, which means it always has to be a whole number. Think of order as the total time it takes to bake an entire cake, whereas molecularity is just the number of eggs you crack in one specific step. Let's zoom all the way back out. Section 5, the real world, putting kinetics to work. And this brilliantly illustrates the immense real-world impact of everything we've just been talking about. Out in industry, mastering kinetics is what gave us the Haber process, which maximizes fertilizer production to literally feed billions of people. In medicine, understanding kinetics is straight-up life-saving. It's exactly how pharmacologists design sustained-release capsules, ensuring a drug enters your bloodstream at the perfect, safe speed. And environmentally, kinetics is how we track the exact rate of ozone depletion and engineer things like the catalytic converters inside our cars. Quick heads up, if you're using this explainer to prep for a big exam, here is your playbook. You want to focus heavily on those rate law formulas and those graph shapes we talked about. Do the numerical problems consistently until it's just muscle memory. But above all else, understand the why. Know exactly how a catalyst hacks that activation energy. Please don't just memorize blindly. If you master the core concepts, I promise you, the math is just going to naturally follow. So, we've unpacked the baseline rules, your physical controllers, the micromechanics of collisions, the heavy math, and the real-world impact. You essentially now know how to control the very speed of chemistry. The question I want to leave you with is this. Now that you understand the true mechanics of momentum, what reactions in your world are you going to accelerate next? Thanks so much for joining this explainer. Keep asking those big questions and keep learning.